All right, now let's look at potential energy. Once again, potential energy has an equation. The equation for potential energy is the mass times the force of acceleration due to gravity times height. Seems pretty easy. Let's pick some parameters, some terms, and solve a problem. I've got one worked out here. So if you got a 2-pound dumbbell, okay, and we're holding this 2-pound dumbbell at a height of 5 feet, just like that, height of 5 feet. So I know that, and I know that, and of course the gravitational acceleration we know. So let's set up a ladder problem. Two-pound mass dumbbell, 5 feet. Two-pound mass dumbbell, 32.2 feet per second squared, 5 feet. Now, what are the units for energy for our general energy equation for potential energy? Foot-pounds force. We clearly don't have that here, so we know we need to convert our units. Right now we have feet squared, pounds mass per second squared. So let's do our foot-pounds mass per pound force second squared. Let's check our units. Pounds mass cancels out. Second squared cancels out. One of the feet cancels out. I'm left with foot-pounds force. I'm pretty sure this is going to work. So looking at our equation before we start plugging numbers, is there anything else we can cancel? The answer is yes. 32.2 is common to both the top and the bottom of our little ladder solving thing. Well, holy smokes, this becomes a real easy problem. 2 times 5. The answer is 10 foot-pounds force. The potential energy of a 2-pound dumbbell held at 5 feet above a reference zero of the ground has 10 foot-pound force, which means if I were to drop that and turn all of that potential energy into kinetic energy, the kinetic energy of that dumbbell as it's falling is 10 foot-pounds force. That's a little more complicated than that because there's acceleration due to gravity, and you have to, once that potential energy is completely converted, that's when the kinetic energy is equal to 10 foot-pounds force. Well, that's interesting. So if I know the potential energy of the thing I'm holding at 5 feet, what if I let go? Well, I know what its kinetic energy is going to be right before it hits the ground. Can I solve for how fast is it going to be going, assuming that all air resistance is negligible, right? Well, let's see. So we said the kinetic energy was, or the potential energy was 10 foot-pounds force. And we know that all of that potential energy is going to get converted to kinetic energy right before it hits the ground. So the potential energy is equals the kinetic energy. Well, the equation for kinetic energy, 1/2 mass velocity squared. Well, what we're trying to solve for is the velocity. So let's rearrange this equation. Kinetic energy, I'm going to bring the 2 over. I'm going to divide by it, and then I'm going to bring the mass over. And then I'm going to take the square, I'm going to bring the square over, but it's missing something. What it's missing is our conversion factor, because you remember the 1/2 mass velocity squared? Or the other way I mentioned you can write it is mass times velocity squared over 2g sub c. This has to be there for your units to work. So to bring the g sub c over, this is our velocity. Now let's set that up in a ladder problem. We know our kinetic energy times 2 times g sub c divided by the mass. Well, do I have everything? Let's see. Pounds mass there it is, pounds force. I've got 2 feet, which is feet squared, and I've got seconds squared, but we still have to take the square root of all that. Is there anything else that can cancel out? Absolutely. So I've got 10 times 32.2, which is 322. Feet squared per second squared, and the square root of that it's hard to write that low, sorry. If you can't see that in the video, I will put it on the screen. The answer, square root of 322 feet squared per second squared is 17.9 feet per second. That's the velocity of that 2-pound dumbbell that we let go of right before it hits the ground, assuming no air resistance.